All right, we were looking at Bohr's model of the atom. We had gone through his first 7 assumptions or propositions for his model, and we were on number 8. So his last few, he has named now the energy, the orbit's energy levels. He's numbered them: n equals 1, n equals 2, n equals 3, etc. Starting with the lowest one, n equals 1, closest to the nucleus. It's the one that has the lowest energy, and as you go up, the energies get higher. He suggested that if an electron was in one level, it could jump up to another by absorbing the exact amount of a photon or a quantum of energy, and if it falls back down, it would have to give that one off. Okay, so number 8 model that we were on, or the number 8 of his model, was that when an electron is in its lowest state, we say it's in the ground state. When E is in lowest state, okay, and remember he was doing hydrogen, so it only had one electron, so it would be in the n equals 1. We say it's in the ground state. Okay, and then to go with that, when an electron is in any level above the ground state, we say that it's in an excited state. And again, remember, this is for hydrogen that only has one electron. If you're looking at bigger atoms, obviously they would have electrons in higher states without them being excited. So when an electron is in any level above ground state, which is n equals 1, we say it's in an excited state. Excited because it's an I think I lost the C in excited there. Excited because, not exit, it's absorbed a quantum of energy and it has jumped up. Let me just fix this word. E-X-C-I-T-E-D. There we go. Okay, so it's in an excited state because it's absorbed a quantum of energy and it's jumped to a higher level. Okay. Number 10, excitation. So jumping up from one level to another. Excitation happens when a photon of energy exactly matches the difference between two levels. Okay, if it doesn't exactly match, it cannot jump from one level to another. So excitation happens when an incident photon, EP, for the energy of an incident photon, corresponds exactly to the difference in energy between the different levels. So corresponds exactly. If it's close, it doesn't matter. It needs to be exactly to difference between two levels. Okay? If it does correspond exactly, then that photon can be absorbed and the electron will jump up. If it doesn't correspond exactly, it will not be absorbed. Okay, and so that leads us to a formula where we are saying the energy of the photon has to equal the difference, right? Delta, the difference in the energy levels. Difference in energy levels. Don't worry, the formula actually has better, so energy of the photon, EP, and we know EP is equal to HF. So HF equals difference is always final minus initial. So we usually write it like this, where the final is where the electron ends up, and the initial is where the electron started. Okay? If when you subtract these two levels, you get a positive energy or positive EP, then it means the electron has been absorbed, right? Because it's going from lower to higher. So this energy, remember we said down here the energy is closer to the nucleus, the energy is lower. So this might be like 2 electron volts for some atom. This might be 4. It does not go like this, by the way. This might be 6. So it starts here and it jumps up to here. your final would be 6 electron volts minus 2 electron volts. You would get a positive 4. The positive indicating that the photon was absorbed. But if it was falling down, then it would be going from 6 to 2. So final would be 2 electron volts. Initial would be 6 electron volts, which would give you negative 4 electron volts. And the negative means the photon was released, okay, or emitted. So a positive on your EP means it's been absorbed, and a negative on your EP means it's been emitted. Okay? And the other kind of cool thing is, right, so an electron in a level will absorb a quantum of energy and jump up here and be excited, but it doesn't stay there very long. It doesn't last long. It falls back down and emits that energy. And remember, one of Bohr's first postulates was what it emits will be the same as what it absorbed. Now, if we go back to the fact that Bohr was saying these electrons could only stay in orbits of certain radii and no others. They could only be in certain orbits around the nucleus. Because he believed that, he spent a lot of time coming up with an equation for the radius, to solve for the radius of these orbits. Okay, so he predicts the radius of the orbits, and you are going to love the equation he comes up with. So predicts radius of orbits for all the different levels for the electrons, but remember, for hydrogen. Okay, so here's the equation. It's R for radius, N for the level, like N equals 1, N equals 2, is going to be equal to h squared, so Planck's constant squared, over 4 pi squared k, that's 8.988 times 10 to the 9th, m, mass of an electron, q, charge on an electron, squared. And this whole thing gets multiplied by the energy level squared. Okay, so where h then is Planck's constant, and so it's going to be 6.626 times 10 to the negative 34. So Planck's constant, and that's joules seconds. K is 8.988 times 10 to the 9th, and that's Newton meters squared per kilogram squared. M is the mass of an electron, 9.109 times 10 to the negative 31 kilograms. Q is the charge of an electron, 1.602 times 10 to the negative 19 coulombs. And no, you don't have to put a negative on the 1.602. Okay, and then N is the energy level, the quantum number of energy level. And so you could figure out the radius of N equals 1 by putting a 1 in here. The second energy level by putting a 2 in, by putting a 3 in. Okay? Now, so this is one. He has 3 equations. This is one. Whoops, the one on the other side, EP equals HF minus HI is another. In his third equation, he actually calculated an equation for the energy levels of all the hydrogen, all the levels in a hydrogen atom. Okay, so energy of levels in hydrogen. Now, this only unfortunately works for hydrogen, but its En is equal to negative 2.17 times 10 to the negative 18 joules. And that's multiplied by 1 over n squared. But remember, we said that a joule is too huge to use when dealing with an energy, when we're talking about electrons and atoms. So we change it to electron volts, and it becomes a much easier number. Negative 13.6 electron volts divided by n squared. With this beautiful equation, we can find the energy of all the different energy levels in hydrogen. Of course, when Bohr proposed this, he was hoping that he would be able to expand it to find them for all the atoms. But really, this is just for hydrogen. Okay?